Welcome to the class. Dear students, today we are going to discuss Kolbe-Schmidt reaction or simply Kolbe reaction. So what happens, which compound shows Kolbe-Schmidt reaction? Phenols show Kolbe-Schmidt reaction. It is the phenol compound that shows this reaction and it involves the introduction of COOH group at ortho position in the ring. Okay, so these are the 2 points. The first point is phenols show this reaction. Second point is it involves the introduction of COOH group, carboxylic acid group at ortho position with respect to hydroxy group in the benzene ring. Let us see what is the reaction. What happens in this reaction is when you passing carbon dioxide gas through sodium phenoxide at 6 atmospheric pressure at a temperature of 125 degrees Celsius, what happens is you get sodium salt of salicylic acid. Sodium salt of salicylic acid or sodium salt of orthohydroxy benzoic acid. Correct? So you get sodium salt of salicylic acid. This followed by acidic hydrolysis yields salicylic acid or orthohydroxy benzoic acid. Orthohydroxy benzoic acid or salicylic acid. So what has happened? Let us repeat. Sodium phenoxide on passing carbon dioxide through sodium phenoxide at a pressure of 6 atmosphere at a temperature of 125 degrees Celsius yields the sodium salt of salicylic acid, which on acid hydrolysis yields salicylic acid or orthohydroxy benzoic acid. Now there are 3 things that I want to say. Kolbe-Schmidt reaction involves introduction of COOH group, carboxylic acid group. As it involves the introduction of carboxylic acid group, this reaction is also called as carboxylation. This reaction is also called as carboxylation. Okay. Second point, as it involves carbonation. Carbonation means addition of carbon dioxide. It involves carbonation at ortho position, right? Carbonation of phenoxide ion, sodium phenoxide ion at ortho position. So because it involves addition of carbon dioxide, it is called as carbonation. Okay, so it is called as carboxylation because introduction of COOH group. It is called as carbonation because carbon dioxide getting added to it. So these are the 2 points. The third point is which is the most important of all point, that is, look at the carbon dioxide structure. This is the structure of carbon dioxide. Positive sign is on this carbon atom. So it is acting as weak electrophile. Thereby it attacks the benzene ring. But had it been only benzene ring, it would not have attacked. Why? Because benzene ring does not have sufficient electron density as to attract carbon dioxide towards it. Only when benzene ring is linked to a electron donor group, a powerful electron donor group such as O- or OH, these are powerful electron donor groups. Only when it is attached to powerful electron donor groups will there be a sufficient electron density at the benzene ring as to attract CO2 towards it. Let me repeat the third point. Had it been only the benzene ring, look at this. It is not possible. CO2 won't attack benzene ring because even though it is an electrophile, it is not a strong, it is a very weak electrophile. So it won't attract that carbon dioxide towards it. So it should have sufficient electron density as to attract carbon dioxide. So that is only possible when it is linked to a powerful electron donor group such as a O-. So this reaction is possible with phenol, but it is not possible with benzene. This is the third point. Now, to understand this reaction in a much better way, let us look into its mechanism. Let us look into the mechanism. So the mechanism here is nucleophilic addition. Nucleophilic addition reaction mechanism. Nucleophilic addition of phenoxide ion to phenoxide ion to your carbon dioxide. Nucleophilic addition of phenoxide ion to carbon dioxide. There are 3 steps in this reaction. Step number 1. Nucleophilic addition and formation of carboxylate ion. Let us see step number 1. Carboxylate intermediate, not ion, intermediate. Let us see step 1. What happens? This is your phenoxide ion, right? Now what can happen? This can come here. So when this electron pair comes here, the carbon here becomes unstable, right? Because its valency is just 4. So what happens? This pair of electron comes outside the ring and appears as a negative charge. So this is the result. Correct? Now let us react it with carbon dioxide. This is carbon dioxide. Correct? Let us react it with carbon dioxide. So nucleophilic addition, which is the nucleophile? This is the nucleophile. So nucleophile addition, this is donated here, and we get an intermediate. There is an H here, C double bond O, O minus, double bond O, fine, and here we go. This is the intermediate. So that is the first step. As you can see, this is the phenoxide ion. This charge now comes as a double bond. When this comes as a double bond, the carbon's valency is not so fit here. So this pair of electron, it appears as a negative charge on the over the benzene ring. Now this is what now attracts carbon dioxide towards it, or this gets attached to carbon dioxide. Nucleophilic addition of phenoxide ion to carbon dioxide. Which is the nucleophile? This is the nucleophile, right? And now it attaches. There is a H here, right? Every carbon has an H. I have highlighted the H here so as to better understand the mechanism. Fine. Okay. Now let us go to step 2. Step number 2. Let me rub this. Step 2. Okay. Step 2. Proton shift in carboxylate intermediate. Proton shift in carboxylate intermediate. Let us understand this. So this is our carboxylate intermediate. Now what happens here is that this is electronegative oxygen. So this pair would come here, right? When this electron pair comes here, oxygen become negative. So the proton here, it goes from here and shifts to oxygen. When this proton shifts to oxygen, this electron pair here, it comes back into the ring. So now what we get is this OH comes here, correct, and COO minus, right? So what happened here? This is the carboxylate intermediate. This shifted to here. This is an electron pair of oxygen. So this electron pair now shifts here. It becomes negative. When it becomes negative, proton shift takes place. When proton shift takes place, this electron pair now comes back into the benzene ring, and what you get is this, that is salt of salicylic acid, right, or salt of orthohydroxybenzoic acid. Step number 3. Step number 3. Acid hydrolysis. Acid hydrolysis of salt, of carboxylate salt. Acid hydrolysis of carboxylate salt. So this carboxylate salt here, now you go for acid hydrolysis, that is H plus H2O, fine, and now what happens? You get salicylic acid. You get salicylic acid. That's it. So that is how these are the three steps of Kolbe-Schmidt reaction: orthohydroxybenzoic acid, salicylic acid. As you have seen, introduction of COOH group at the ortho position with respect to hydroxy group of the benzene ring. Right? Now let us discuss about the significance of Kolbe-Schmidt reaction. Significance. What is the significance? Okay. So we can prepare, this is salicylic acid. So we can make aspirin through salicylic acid, right? How do we make aspirin? Just react it with acetic anhydride in catalytic amount of H2SO4. So now you get acetyl salicylic acid, right? That's it. So you have made aspirin or acetyl salicylic acid by using salicylic acid. So you can make indirectly aspirin from Kolbe-Schmidt reaction, correct? For making aspirin, first of all you have to make salicylic acid using Kolbe-Schmidt reaction, and after making salicylic acid you have to treat it with acetic anhydride, reflex it in catalytic amount of H2SO4, you get aspirin. So it is indirectly used in the preparation of aspirin, and aspirin, you know, it is an anti-inflammatory analgesic drug, and it has also got platelet aggregation. It is platelet aggregation inhibitor. So it's a very important drug. So you can make it through this reaction. The second thing is, see, if you are using, in place of this, if you are using this, that is 3-naphthol, this is naphthalene, and this is naphthol, 3-naphthol, this is 1, 2, 3. If you are using 3-naphthol and if you are going for carbonation at same conditions, 6 atmosphere, 125 degrees Celsius, if you are going like that, what is this thing? Carboxylation will occur and carboxylic acid will be introduced into this position. The product will be like this. Okay, if you are going for carbonation of 3-naphthol using same condition, carboxylic acid will be introduced, of course, at the ortho position, and the end product that you get will be this. So this is now 1, 2, 3. 3-hydroxy, 2-naphthoic acid. 3-hydroxy, 2-naphthoic acid. So it is a dye. It is used as a dye. It is a very important dye which is used in textile industries. So it is a very so this dye you can prepare through Kolbe-Schmidt reaction. Now there is another thing that you can prepare through Kolbe-Schmidt reaction. For that you have to change the reaction condition. Take the same phenol, go for carbonation, use same condition, 6 atmosphere pressure, and use higher temperature, 225 to 250 degrees Celsius. If you are using temperature, then you get COOH at para position and not at ortho position. At para position you will get. Okay, para isomer, to make para isomer, it's higher energy activation. Energy of activation is much higher for para isomer. So that energy of activation we are giving by increasing the temperature. So when we give that kind of temperature, we get the para isomer. This is para hydroxybenzoic acid. Now para hydroxybenzoic acid is precursor of parabens. It is a precursor of parabens which is used as in cosmetic industry. Parabens. It is used in cosmetic industry as a preservative. So you can make parabens using Kolbe-Schmidt reaction. Dear students, I hope you have liked the class. If you have done so, please do not forget to subscribe the channel. Share it, like it, and share it with your friends. Thank you very much.